Stop calling Mars a dead planet. It is not dead, it is dying. Right now, today, while you are watching this. While scientists are reviewing data from 4 separate orbiters parked in its orbit, while engineers at JPL are sending commands to a rover sitting in a crater on its surface, while agencies on 3 continents are actively debating whether to send human beings to live on it, Mars is losing water into space in real time, and we just found out the mechanism is worse than anyone predicted. The word dead implies something is over, done, a conclusion reached, a process completed, a chapter closed. Dead planets do not have weather. They do not have active chemistry. They do not have mechanisms still stripping material off their surfaces and injecting it into space at rates that vary by a factor of 100 depending on what the weather is doing on any given day. Mars has weather. Mars has chemistry. Mars has a process of active atmospheric loss that is ongoing, variable, seasonally driven. And as a paper published in Communications, Earth and Environment in February of 2026 just demonstrated, triggered by events we did not even think counted as significant until we watched one happen in real time and measured what followed. The story that science has been telling about Mars is a past tense story, a tragedy in the passive voice. Mars had an ocean. Mars had a magnetic field. Mars lost its atmosphere. Mars became cold and dry. All of it in the completed past. All of it over. All of it filed under the broad category of how planets die, a cautionary tale, a forensic case study, a relic of ancient violence preserved in the geological record. And the story is compelling in that form. It is a genuine tragedy. The scale of what Mars lost, a global ocean covering perhaps 1/3 of its surface, a dense atmosphere warm enough to sustain liquid water, a magnetic field powerful enough to shield both from the solar wind, and possibly, the beginning of biological chemistry in the warm pools and river deltas and lake beds that we are still finding the traces of billions of years later. The scale of that loss is staggering. It deserves its place in the canon of planetary tragedy. But telling it only in the past tense is incomplete, and the incompleteness matters not just for scientific accuracy, but for what we are planning to do about Mars. When you tell a story only in the past tense, the crime is over. The perpetrator has left. The scene is cold. You can study it at your leisure. There is no urgency. When you tell the story in the present tense, everything changes. The story that science has been telling about Mars is a past tense story, a tragedy in the passive voice. Mars had an ocean. Mars had a magnetic field. Mars lost its atmosphere. Mars became cold and dry. All of it in the completed past. All of it over. All of it filed under the broad category of how planets die, a cautionary tale, a forensic case study, a relic of ancient violence preserved in the geological record. That story is not wrong, but it is incomplete. It is missing the present tense. Mars is still losing water, right now. It lost water during a regional dust storm in August 2023 that covered 1.2 million square kilometers of the northwestern Syrtis Major region. It lost water in a way that spiked hydrogen escape rates at the exobays, the boundary between the atmosphere and space, to 2.5 times the levels measured during the same season in previous years. It lost water in a way that no existing climate model predicted was possible during the Northern Hemisphere summer, in the season that was supposed to be quiet, in the season that scientists had written off as a minor contributor to the planet's ongoing dehydration. The planet bled through a wound we did not know it had, a wound that opened during a season we thought was quiet, during a storm type we thought was too small to matter, in a way that our best climate models did not predict and had not been observed with this level of clarity and causal completeness in nearly 2 decades of continuous Mars observation. This is the live crime scene. This is the live crime scene. The perpetrator is not a distant historical event, but a physical process operating continuously, operating today, discovered to operate more aggressively than we realized in a season we thought was quiet. The instruments are recording. The spacecraft are watching. The scientists are analyzing. The papers are being written. And we are planning to move there. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Before the present tense horror, let us establish the crime that has already been committed. Because to understand what is still happening to Mars, you need to understand what has already been done to it, the full, multi-billion-year sequence of catastrophes that converted one of the most potentially habitable worlds in the solar system into a near-vacuum desert, with an average surface temperature of minus 60 degrees Celsius and an atmospheric pressure 1% of Earth's. Mars is a rocky planet. It formed from the same disk of gas and dust that formed Earth, from the same raw materials, at roughly the same time, approximately 4.5 billion years ago. It is smaller than Earth, half the diameter, 1/10 the mass, which turns out to matter in ways that are both subtle and catastrophic. But it started, as far as we can tell, with the ingredients that matter most for habitability. It had heat, it had water, it had a magnetic field. That last one, the magnetic field, is where the story begins to go wrong. Earth's magnetic field is generated by the motion of liquid iron in its outer core, a process called the geodynamo, driven by the temperature gradient between the extremely hot inner core and the cooler mantle. Combined with Earth's rotation, the fluid iron moves in complex patterns, and those patterns generate electrical currents, and those electrical currents generate the magnetic field that extends from Earth's core outward into space, deflecting the charged particles of the solar wind, the continuous stream of plasma emanating from the sun, and protecting the atmosphere from being stripped away. Mars had a magnetic field. We know this because the geological record is written in rocks. The iron-rich minerals in ancient Martian rocks, rocks that solidified from molten material billions of years ago, were magnetized when they cooled, locking in the direction of the magnetic field that existed at the time. This remnant magnetization is visible today in Mars Global Surveyor's magnetic field measurements and in the analysis of Martian meteorites that have fallen to Earth. The rocks tell us there was once a global magnetic field, a dynamo operating in the core, generating a field that, at least for a while, kept the planet's atmosphere intact. And then it stopped. The core of Mars solidified. This is the catastrophe, simple, irreversible, and a direct consequence of being smaller than Earth. A smaller planet has less internal heat. A smaller planet cools faster. A smaller planet reaches the critical threshold at which the core transitions from liquid to solid much sooner than a larger one. When the liquid iron core of Mars solidified, or when its convective circulation became too sluggish and stratified to sustain the dynamo, the geodynamo died. The exact timing is still debated. For years, the consensus was that the Martian dynamo collapsed approximately 4.1 billion years ago in the early Noachian period, the epoch corresponding to the heaviest asteroid bombardment in solar system history. But a 2024 paper in Nature Communications from Harvard's Paleomagnetics Lab, using a quantum diamond microscope to analyze iron sulfide minerals in the Allen Hills 84001 meteorite, a famous Mars rock collected from Antarctica in 1984 and at the center of the 1996 controversy over possible fossil life, found that the remnant magnetization of those minerals indicated the field persisted until at least 3.9 billion years ago, 200 million years later than previously thought. 200 million years might sound marginal. It is not. 200 million years is the difference between a dynamo that died before the late heavy bombardment, the era of intense comet and asteroid impacts, and one that persisted through it. It means the magnetic field survived the worst meteorological and geological violence the young solar system could produce, and died afterward, when things had calmed down somewhat. It means the window during which Mars had both a magnetic field and liquid water was longer than anyone had assumed. Life had more time, but the field died, and when it did, the protection died with it. The solar wind is not a metaphor. It is a physical thing, a continuous stream of charged particles, primarily protons and electrons, blowing outward from the Sun at speeds between 400 and 800 kilometers per second. At Earth's distance, the solar wind carries a particle density of roughly 5 to 10 particles per cubic centimeter, and an energy that, over geological time, is more than sufficient to strip an unprotected atmosphere. Earth is not unprotected. Earth's magnetic field deflects the solar wind not perfectly, and not without complex interaction at the poles and in the magnetopause, where the field boundary meets the solar wind, but effectively enough that our atmosphere has been preserved across 4.5 billion years of continuous solar wind exposure. The magnetic field is the shield. The atmosphere is what the shield protects. When Mars lost its shield, the solar wind had direct access to the upper atmosphere. The mechanism of atmospheric loss is complex, involving multiple pathways, multiple physical processes, each one stripping material in slightly different ways. Ion escape. The solar wind's electric and magnetic fields accelerate ions in the Martian ionosphere and fling them into space. Sputtering. Solar wind particles physically knock atmospheric atoms loose through collision, like billiard balls hitting other billiard balls. Photodissociation. Ultraviolet radiation from the sun breaks molecular species like water and carbon dioxide into their constituent atoms, producing lighter, faster atoms more likely to exceed Mars's escape velocity. And thermal escape, the gene's escape process, in which the high-energy tail of the thermal velocity distribution of a light atom like hydrogen at the top of the atmosphere, where collisions are rare, has enough velocity to escape Mars's gravity well entirely. NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, which has been orbiting Mars since September 2014, has been measuring these escape rates continuously for over a decade. The numbers from MAVEN are clear. Approximately 2 to 3 kilograms of atmospheric material escapes from Mars every second, per second, continuously. 2 to 3 kilograms per second. Spread across 4.1 billion years of atmospheric escape at present-day rates, with the caveat that rates were much higher early in Martian history when the Sun was more active, the equivalent of a global layer of water approximately 23 meters deep over the entire surface of Mars, and that is the conservative, present-day rate estimate. The actual historical loss was greater early in solar system history. When the young Sun's ultraviolet output was much higher, escape rates were correspondingly higher. The total water lost over Martian history is estimated at enough to cover the planet in a global ocean 380 to 970 meters deep, up to a kilometer of water, globally averaged, stripped away over billions of years. Mars once had a kilometer of ocean. The key word is once. But, and this is the crucial shift, the loss did not stop when the magnetic field died. The loss did not stop when the atmosphere thinned. The loss did not stop when the liquid water froze. The loss is ongoing. It is happening today, at 2 to 3 kilograms per second. And the 2026 study has shown that it is happening at rates that are far higher than baseline during specific events that we now understand are more common and more effective than any previous model predicted. Let us make the August 2023 storm real. The 21st of August, 2023. Mars Reconnaissance Orbiter's wide-field camera, the Marquee instrument, designed to produce daily global maps of the Martian surface, records something unusual beginning to develop in the northwestern Syrtis Major region. Syrtis Major is one of the most recognizable features on Mars, a dark, roughly triangular volcanic shield, visible even through amateur telescopes on Earth. First mapped by the Dutch astronomer Christiaan Huygens in 1659, the oldest feature on Mars ever captured in a telescope image. Dust is lifting from the surface around this ancient volcanic region. A regional storm is forming, not the massive planet-encircling global storms that shut down the Opportunity rover's solar panels in 2018 and killed it by cutting off its power, but a regional event, the kind that covers millions of square kilometers of the Martian surface but does not spread globally. Regional storms are common on Mars. They happen multiple times per Martian year. They are, in the standard model of Martian atmospheric science, considered interesting but not particularly significant contributors to long-term water loss. The really important storms in the previous scientific understanding were the global ones. The regional ones were secondary players, background noise. By August 22nd, the storm covers 1.2 million square kilometers. For scale, 1.2 million square kilometers is larger than Egypt. Larger than Texas, New Mexico, Arizona, California, Nevada, Utah, and Colorado combined. A weather system the size of most of a continent, lifting dust from the Martian surface and driving it into the atmosphere in a churning, wind-sheared mass of red-brown particles. Here is what happens inside a Martian dust storm that makes it more than just a weather event. The dust particles, tiny grains of iron oxide, the rust that gives Mars its colour absorb sunlight. They heat up, and because they are suspended throughout a column of atmosphere kilometres deep, they heat that column of atmosphere from within. The temperature of the middle atmosphere, the region between roughly 30 and 80 kilometres altitude, rises dramatically as the absorbed solar energy radiates from the dust into the surrounding gas. Hot air rises. This is basic physics. In a planet's atmosphere, when a column of air heats up, it begins to convect upward. The heated middle atmosphere in a Martian dust storm begins to rise, and as it rises, it carries with it whatever is mixed into it. Water vapour from the lower atmosphere, which normally stays close to the surface, and the lower atmospheric layers where temperatures are cold enough to allow condensation and recycling water vapour that is normally trapped below the condensation level and return to the surface as frost or ice clouds before it can reach the altitudes, where it would be vulnerable to photodissociation. That water vapour is physically lifted by the convective currents of the heated atmosphere and transported upward, up through the condensation level, up through the region where it would normally rain out or freeze, up into the middle and upper atmosphere where temperatures and pressures are too low for condensation, where the water vapour cannot recycle back to the surface because there is nothing to condense on, where the ultraviolet radiation from the sun is intense and unfiltered, where photodissociation splits the water molecules into hydrogen and oxygen, and then the hydrogen escapes. The hydrogen atoms, produced by the photodissociation of the water molecules the storm has lofted, are the lightest atoms in existence. Mars's gravity, 38% of Earth's surface gravity, imposes a relatively modest escape velocity of about 5 km per second at the surface, dropping to roughly 4 km per second at the exobase. Hydrogen atoms at the temperatures of the Martian upper atmosphere have a thermal velocity distribution that puts a significant fraction of them above the escape velocity. They leave the atmosphere and enter space. Permanently. They do not come back. The ExoMars Trace Gas Orbiter's NOMAD instrument detected the surge in water vapour at altitudes above 40 kilometres, beginning just days after the storm initiated on August 21st and 22nd. The Emirates Mars Mission's Hope probe, the UAE's first interplanetary spacecraft, orbiting Mars in its unique high elliptical orbit designed for studying the full vertical structure of the atmosphere, measured the consequence: a dramatic spike in hydrogen concentration at the exobase. Hydrogen levels at the exobase rose to 2.5 times those recorded during the same northern summer season in previous years. The escape rate, the rate at which hydrogen was bleeding from Mars into space, was elevated for weeks after the storm itself had dissipated. Adrián Brines, of the Centro de Astrobiología in Madrid and lead author of the February 2026 study, described what they found in terms that capture the specific scientific surprise. This water enhancement was not predicted by existing climate models, and the season in which it occurred, Northern Hemisphere summer, was considered to play only a minor role in water loss compared to the dusty southern summer season. Not predicted by existing climate models, in a season considered to play only a minor role, these three phrases taken together describe the specific quality of the discovery. It is not a small refinement to a well-understood process. It is a new pathway, a mechanism that existing models did not contain, an escape route for Martian water that the scientific community had not, in the decades of Mars atmospheric research preceding this observation, correctly identified or quantified. Let us understand the full architecture of the crime. There are, in the current scientific understanding, at least 3 distinct seasonal windows during which water loss from Mars is elevated. The traditional picture had one primary window, Southern Hemisphere summer. The new picture has 3. Window 1. Southern summer, when Mars is at perihelion, its closest point to the Sun, which coincides with Martian Southern Hemisphere summer. The atmosphere is at its warmest and dustiest. The obliquity of Mars, its axial tilt, approximately 25 degrees, similar to Earth's 23.5 degrees, means that the Southern Hemisphere receives concentrated solar radiation during this period, and the Martian climate enters its dusty season. Water vapour is transported to high altitudes by the general circulation, and the hydrogen escape rate rises dramatically by a factor of 10 or more compared to the quiet northern summer baseline. MAVEN has been measuring this seasonal spike since 2014. It was known, it was expected, it was in the models. Window 2. Global dust storms. When a regional storm escapes its local geography and spreads to encircle the entire planet, as happened in 2007, and again in 2018, the atmospheric warming is global and the water transport is global. The 2018 global storm, which killed the Opportunity rover by blocking sunlight from its solar panels for months, also drove a massive spike in hydrogen escape detectable by MAVEN and by ESA's Mars Express orbiter. Water vapor rose to altitudes above 80 kilometers, the upper mesosphere where photodissociation is essentially complete. The 2007 global storm showed a 100-fold increase in water vapor in the middle atmosphere. Global storms are the most dramatic acute water loss events on Mars. They were known, they were expected, they were in the models. Window 3. Anomalous regional storms. This is the new one. The August 2023 storm. The discovery of 2026. A regional storm not global, not during the peak dust season occurring in the northern hemisphere during northern summer, a season previously considered too cold and too stable for significant water transport to the upper atmosphere. The storm was unusually intense for its season and location, but it was not exceptional by the standards of Martian dust activity in general. It was, by the yardstick of Martian weather, a moderately remarkable regional event. Not the worst thing that happens on Mars, not even close to the worst. And it drove water loss rates at the exobase to 2.5 times the previous year baseline. The crucial implication: if a moderately remarkable regional storm during the quiet season can produce water loss rates 2.5 times the baseline for weeks, then the cumulative contribution of all the regional storms that occur throughout the Martian year, some during the quiet season, some during the semi-active season, some during the peak season, has been systematically underestimated. The previous models only accounted for the southern summer window and the occasional global storm. The regional storm window was missing. How much missing? The researchers' analysis suggests that the water loss during the 2023 northern summer storm, while a factor of 2 lower than the massive rates seen during global southern storms, was still a massive spike relative to the usual northern summer baseline. Multiplied across the frequency of regional storms which occur regularly, multiple times per Martian year, at various locations and seasons, the accumulated water loss from this previously uncounted mechanism is potentially significant. Not as large as the global storm contribution, but not negligible either. A missing piece of the planet-wide budget. The budget of water loss is being revised upward. Now let us talk about the crime scene. Let us walk through what Mars looks like today, examined as a forensic record of the catastrophe that the ongoing loss represents. The present surface of Mars is inhospitable to liquid water in a way that is not primarily about temperature, though the average temperature of -60 degrees Celsius is well below water's freezing point, but about pressure. The Martian atmosphere has a surface pressure of approximately 600 to 700 pascals. Earth's sea level atmospheric pressure is 101,325 pascals. Mars has less than 1% of Earth's surface atmospheric pressure. At this pressure, liquid water cannot exist. Not because it would freeze, though it would, eventually, but because of the phase diagram of water. At pressures below the triple point of water, 611.73, Pascal's liquid water is not a stable phase. Below this pressure, water can exist only as solid ice or water vapor. There is no pressure at which liquid water can form on the surface of present-day Mars. Any ice that warms above the freezing point does not melt into liquid. It sublimates directly from solid to gas. The rivers that carved the channels visible in satellite imagery across the Martian surface, channels hundreds of kilometers long, with tributary networks, meander patterns, and delta structures that speak unmistakably of sustained liquid flow. Those rivers flowed when the atmosphere was thick enough, and the temperature warm enough, and the pressure high enough for liquid water to exist. When Mars had a magnetic field, when Mars had a denser atmosphere, when Mars was a different kind of world. The geological record of that world is extraordinary. The PNAS study, published in December 2025, mapping Martian river basins across the global surface, found that Mars had watershed systems dwarfing anything on Earth. drainage basins comparable in scale to entire continents, carrying water from highland regions into the great northern lowlands where the ancient ocean sat. The oldest watershed systems date to the Noachian period, more than 3.7 billion years ago. The youngest evidence of liquid water isolated, episodic, perhaps subsurface fed maybe as recent as 2 billion years ago. The ocean in the northern hemisphere was real. Multiple independent lines of evidence, shoreline topography, mineralogy, sediment chemistry, the distribution of ancient erosion features, all point to a body of water in the northern lowlands that was, at minimum, comparable in volume to the Arctic Ocean. Some estimates suggest it covered roughly 1/3 of the Martian surface to an average depth of several hundred meters. That ocean is now a thin film of ice, buried under Martian dust in the regolith and concentrated at the poles. Some of it was lost to space, broken down into hydrogen and oxygen by the same photodissociation process that continues today, the hydrogen escaping and the oxygen reacting with the iron in the surface rocks to produce the iron oxide that gives the planet its rust-red colour. Some of it was incorporated into hydrated minerals, clay minerals, sulfates, carbonates, the chemically altered rocks that the Curiosity and Perseverance rovers have been driving through for years. The rust is the water's obituary. Every iron oxide particle on the Martian surface is evidence of where water used to be. Every red grain of Martian dust carries the chemical fingerprint of a world that once had an ocean and spent billions of years converting it into the material that makes the planet look, from space, like a drop of blood. There is a number that is worth sitting with. The water inventory study published in the Journal of Geophysical Research, Planets in 2024, led by Bruce Jakosky at the University of Colorado, the same Jakosky who is the principal investigator of the MAVEN mission, systematically quantified every identifiable sink for Martian water, lost to space, formation of hydrated minerals, remnants of the ancient ocean now frozen in the polar caps and shallow ground ice, possible deep crustal groundwater or ice. The total, across all sinks, was 380 to 970 meters of global equivalent layer, meaning the total water Mars has lost, if spread uniformly across the entire surface, would form a layer 380 to 970 meters deep, possibly up to 1,970 meters if deep crustal reservoirs are included. For comparison, the Earth's surface and near-surface water inventory, scaled to Mars's surface area, would be 1,400 meters. Mars had, at minimum, the equivalent of about a quarter of Earth's water inventory, possibly more, possibly considerably more, and almost all of it is gone. The present-day escape rate, 2 to 3 kilograms per second, plus the elevated rates during dust storms and the newly discovered regional storm pathway, is small compared to the rates that operated early in Martian history. Most of the water loss happened in the first billion years, when the Sun was more active, when Mars's atmosphere was thicker and the escape rate was correspondingly higher, when the magnetic field was dying and the shield was failing. But the small present-day loss is not zero, and the newly discovered contribution of out-of-season regional storms means that the small present-day loss is larger than the models said. Mars is still bleeding, not hemorrhaging, not collapsing, not in the final acute crisis of a dying world. The catastrophe happened billions of years ago. What is happening now is the slow, systematic, continuous final drainage of a world that was already crippled. Before the rocket storm mechanism, let us also talk about what the surface of Mars actually looks like through the lens of the ongoing dying, because the surface is the crime scene, and walking through it forensically reveals the full scale of what has been lost. Mars is a world of extraordinary geological diversity. It has the tallest volcano in the solar system, Olympus Mons, a shield volcano 22 kilometers high and 600 kilometers wide, broader than France. It has the longest and deepest canyon system in the solar system, Valles Marineris, a canyon network stretching nearly 4,000 kilometers along the Martian equatorial region, 7 kilometers deep, so large that standing at the rim and looking across would give you no view of the opposite wall, which would be below the horizon. It has the largest confirmed impact crater in the solar system, Hellas Planitia, an impact basin in the southern hemisphere, roughly 2,300 kilometers wide and 7 kilometers deep. The scar of an asteroid collision so violent that the shockwave likely temporarily thickened the Martian atmosphere and may have played a role in maintaining liquid water long enough to leave the geological traces we observe in its interior. All of this violence, all of this geological diversity, all of this dramatic topography and the overriding dominant feature of the planet is not the volcanoes or the canyons. It is the dust. Mars is red because it is rusty. The iron oxide that coats the surface is the product of billions of years of chemical reactions between iron-bearing minerals in the crust and the tiny amounts of water that have been cycling through the atmosphere and surface. The rust is evidence of water. Every red grain of Martian dust is a record of a water molecule that once touched this surface and was broken apart, its oxygen combining with iron, its hydrogen escaping to space. The colour of Mars is the colour of its crime. The regolith, the layer of loose, fragmented material covering the bedrock, is not uniform. In some areas, it is fine-grained dust. In others, coarser gravels and rocks shattered by billions of years of thermal cycling and meteorite impacts. The Perseverance rover, exploring Jezero crater since 2021, has driven through ancient river delta deposits, sedimentary rock laid down in layers by water flowing into the crater billions of years ago, and is collecting samples for eventual return to Earth. The samples will tell us, with a precision no orbital observation can match, exactly what the chemistry of that ancient water was, and exactly how long ago it last flowed. The polar ice caps are the most visible remaining water inventory. The North Polar Cap is a layered structure, a stack of ice and dust layers deposited over millions of years of climate cycles, recording the history of Martian climate variation the way tree rings record Earth's climate. The South Polar Cap is similarly layered, but its surface is permanently covered by a thin cap of frozen CO2 that never fully sublimes even during summer. Below the surface, ground ice extends from the poles down to mid-latitudes, detectable by orbital radar and directly confirmed at high northern latitudes by the Phoenix lander, which used a robotic arm to scrape the top few centimeters of regolith in 2008 and revealed bright white ice directly below the surface, watching it sublime in the thin atmosphere within minutes of exposure to the sun. This is the surviving water inventory. Polar caps, subsurface ice at mid-latitudes, hydrated minerals locked in the ancient altered crust, and the whisper of water vapor in the thin atmosphere, 21 micrometers of global equivalent depth, half the width of a human hair. This is what 4.5 billion years of stripping has left. This is the remainder after the ocean, after the rivers, after the lake systems, after everything that was once there. And it is still slowly going. The MAVEN mission deserves its own section in this story, because without MAVEN, the 2026 discovery would have lacked its baseline, its context, its ability to say 2.5 times higher than previous years, rather than just high. MAVEN is the instrument that made the comparison possible. MAVEN launched on the 18th of November, 2013, and entered Mars orbit on the 21st of September, 2014. It was designed specifically to study the Martian upper atmosphere and measure the rate at which it is being lost to space. The first spacecraft ever dedicated to understanding Mars's atmospheric escape in comprehensive, systematic, long-term detail. The science questions MAVEN was built to answer are precisely the ones the 2026 study addresses. How much gas is being lost from Mars's atmosphere today? What are the processes driving that loss? How do the current loss rates connect to the past, to the era when Mars had a thick atmosphere and liquid water? What was the climate history of Mars, and why does it look the way it does today? In the 12 years MAVEN has been operating in Mars orbit, it has accumulated a dataset of atmospheric escape rates that is unmatched in the history of Mars science. It has measured the seasonal variation, the tenfold increase in hydrogen escape between the quiet northern summer and the active southern summer, driven by the seasonal asymmetry of Martian water transport. It has measured the response to solar energetic particle events, the sudden, intense bursts of radiation from solar flares and coronal mass ejections that temporarily spike the atmospheric escape rate by additional factors. It has watched two global dust storms, 2018's killer storm and the 2007 event in the retrospective MAVEN data analysis, and documented their effect on water loss. And it has been there since 2014, accumulating the multi-year baseline of measurements that allowed the 2023 northern summer anomaly to be recognized as anomalous. Without a decade of MAVEN data showing what hydrogen escape looks like during normal northern summers, there would be no 2.5 times higher than usual to report. The discovery of the new escape pathway required the context that only a decade of continuous monitoring could provide. The MAVEN mission has been extended multiple times beyond its original one-year primary mission. It is currently, in 2026, operating in its extended mission phase, still returning data, still measuring the ongoing escape of Mars's atmosphere. It is the long-running surveillance of a dying planet, conducted from orbit by an instrument that has outlasted its original contract by a factor of 12 and is still working. This is what science looks like at its best. Patient, long-term, systematic observation of something that changes slowly, using data accumulated over years to detect changes that would be invisible in any shorter window. Let us also talk about what happens during a Martian global dust storm at the level of human experience, because regional storms like the August 2023 event are dramatic. But the global storms that have defined the worst periods of water loss in the recent geological record are something categorically more severe. A Martian global dust storm is one of the most extreme weather events in the solar system. Not in terms of wind speed, Martian winds are actually relatively gentle compared to Earth's hurricanes, because the thin atmosphere has far less mass to accelerate, and even at high speeds carries little kinetic energy. The famous fear of Martian winds in science fiction depicted as the catastrophic event in The Martian is somewhat overstated. A 100 kilometer per hour. Martian wind has the force of roughly a 10 kilometer per hour. Earth breeze. The threat from global dust storms is not the wind, it is the light, or rather the absence of it. During the 2018 global dust storm, the solar panels of the Opportunity rover, which had been operating successfully for 14 years on the Martian surface, far beyond its design 90-day mission, were covered by a sky so thick with suspended dust that the solar energy reaching the surface dropped to near zero. Opportunity had been sending regular transmissions home from Endeavour crater. After the storm began intensifying, the transmissions became less frequent as the rover powered down non-essential systems to conserve dwindling battery reserves. Then they stopped. NASA waited. The storm eventually subsided. The sky began to clear. Engineers hoped that the Martian winds would clean the dust off Opportunity's panels, a phenomenon that had saved Opportunity multiple times before, when dust accumulated and then was removed by a gust that restored the panels to full efficiency. Cleaning events, engineers called them. A kind of Martian luck that had kept Opportunity alive for years beyond its design life. The cleaning event did not come this time, or if it did, it was not enough. Opportunity never woke up. On the 13th of February 2019, NASA declared the mission complete after one final attempt to contact the rover. Produced no response. The storm had killed it. But before it killed the rover, the storm did something to Mars's atmosphere that the rover's death overshadowed in public attention. The same storm that powered down Opportunity drove a massive pulse of water into the upper atmosphere. MAVEN detected the spike in hydrogen escape. Mars Express detected the elevated water vapor altitudes. The global storm of 2018 was, in terms of atmospheric water loss, one of the most significant single events in the recorded history of Mars atmospheric science. And the 2023 regional storm, which was by any measure far less severe than the 2018 global event, still drove water loss at 2.5 times the northern summer baseline. If a global storm like 2018 can happen while human beings are living on Mars, and it will, because global storms occur roughly every 3 to 5 Martian years, and have done so throughout recorded history, the dual threat becomes clear. The storm threatens both the equipment that keeps humans alive, solar power systems, dust-covered habitats, clogged mechanical systems, and the water inventory that humans would be relying on, by accelerating the ongoing loss of accessible surface and near-surface ice through the rocket storm mechanism. These threats operate on different timescales. The immediate threat to equipment is acute hours to days. The threat to the water inventory is geological centuries to millennia. but both are real, and the 2026 study has made one of them more quantitative and more undeniable. Let us talk about rocket storms, because the February 2026 paper introduced this concept, and it is important enough to understand it precisely. The term rocket storm, used by some science communicators to describe what was observed in August 2023, refers to the specific mechanism by which a localized Martian dust storm can function as a launching mechanism for water vapor. The analogy to a rocket is this. A rocket works by rapid heating, creating upward thrust. A rocket storm on Mars works by rapid heating of the middle atmosphere, creating upward convective thrust, powerful enough to lift water vapor above the hygropause, the altitude at which water vapor normally condenses out of the atmosphere and is returned to the surface. In a normal Martian atmosphere during northern summer, the hygropause sits at relatively low altitudes around 20 to 30 kilometers. Water vapor rising from the surface encounters this condensation barrier and is converted to ice crystals that eventually fall back to the surface. The hygropause is, in effect, a ceiling preventing water from reaching the upper atmosphere during the quiet season. The August 2023 storm broke through this ceiling. The intense heating of the middle atmosphere by the suspended dust, 1.2 million square kilometers of dust, absorbing sunlight and re-radiating it as heat into the surrounding atmospheric column, drove temperatures above the hygropause level high enough that the condensation barrier temporarily dissolved. The hygropause altitude rose, or the temperature above it rose enough to keep water in vapor form. The convective updrafts from the heated atmosphere physically carried water vapor through the ceiling and into the upper atmosphere. Once above 40 to 60 kilometers, the water vapor was in direct contact with solar ultraviolet radiation. Photodissociation. Water molecule absorbs a UV photon and breaks apart. One oxygen atom. Two hydrogen atoms. The oxygen, being heavier, tends to remain in the atmosphere and eventually combines with surface minerals. The hydrogen atoms, being the lightest atoms in the universe, enter the thermal escape process. At the exobase, roughly 150 to 200 kilometers above the surface, those hydrogen atoms with thermal velocities above Mars's escape velocity simply leave. They flow upward into space, drawn by the planet's gravity but having enough kinetic energy to escape it. This is the crime in progress. This is the mechanism being applied to the crime in progress. Right now, every time a regional storm develops on Mars, every time a patch of the Martian surface large enough and dusty enough generates a convective column powerful enough to push water above the hygropause, Mars bleeds. The rate varies by a factor of 100 across the Martian year, according to 2 years of Mars Express observations of hydrogen escape rates compared between a storm year and a quiet year. 100. The maximum water loss rate is 100 times the minimum. And the newly discovered out-of-season pathway from regional storms like the August 2023 event means that the annual cycle has more high-rate periods than the previous models captured. This is not abstract. This is happening right now, in real time, on a planet currently hosting 5 active spacecraft and 1 active rover, a planet that 6 space agencies have active missions at, a planet that multiple commercial companies and at least 2 national space programs are actively planning to send humans to within the next decade. And now the pivot that the angle of this story demands. We are planning to move there. Not as a metaphor for scientific interest, not as a distant aspiration, as a concrete operational goal with funding, hardware development, launch windows, and trajectory calculations. SpaceX has stated a goal of launching uncrewed Starship missions to Mars as early as 2026, with crewed missions in the late 2020s or early 2030s. NASA's Moon to Mars architecture calls for human Mars missions in the 2030s. China has stated ambitions for Mars in the 2030s as well. The people planning these missions know about the dust storms. They know about the thin atmosphere. They know about the radiation. The surface of Mars, unprotected by a significant magnetic field, receives radiation doses roughly 100 times higher than at Earth's surface, with periodic spikes during solar energetic particle events that would require shelter in radiation-hardened structures. They know about the perchlorate-contaminated soil toxic oxidizing compounds distributed widely across the Martian surface that would be dangerous to human health if inhaled or ingested. They know about the dust that can cover solar panels and clog equipment and settle into the mechanisms of rovers and will do the same to human habitation systems. What they may have underestimated, what the February 2026 study is revising, is the timeline. Not the timeline of human missions, the timeline of the planet itself. If the present-day water loss rate is higher than models predicted, if the regional storm pathway has been adding to the loss budget in ways that were not counted, then the estimate of how much water remains accessible on Mars is more uncertain than previously thought. The polar caps and shallow ground ice represent the main accessible water inventory for any future human missions. If those reservoirs are being depleted at a higher rate than the models indicated, the resource picture changes. This is not a crisis in the sense of the water will run out before humans arrive. The accessible ice reservoirs represent enormous quantities of water. Estimates of the polar caps alone suggest they contain enough water ice to cover the entire planet in a layer 30 to 35 meters deep. The present-day loss rate, even at the upper estimate including storm-enhanced pathways, is tiny compared to this reservoir. Humans would not notice the daily loss, but the principle matters. The principle is this: we are planning to go to a planet we do not yet fully understand. We are planning to rely on resources, primarily water, primarily from the ice that we have not fully characterized in terms of their accessibility and their depletion rate. The 2026 study is not the last revision we will make to our understanding of Martian water loss. It is one more in a series of revisions, each one making the picture more complex, each one adding a previously uncounted mechanism, each one incrementally revising the budget upward. Every time we add a new mechanism, we make the water picture slightly less comfortable. There is one more piece of the mechanism that deserves careful attention. The piece that makes the August 2023 discovery particularly alarming for planetary scientists who had been telling a reassuringly tidy story about when Mars loses water and when it doesn't. The story was seasonal. Southern summer, dusty season, water loss elevated. Northern summer, quiet season, water loss minimal. This was not arbitrary. This was based on well-understood atmospheric physics. Mars's orbit is more elliptical than Earth's. Its eccentricity is 0.093 compared to Earth's 0.017, meaning Mars's distance from the Sun varies more across its orbit. When Mars is at perihelion closest to the Sun, it is in its southern hemisphere summer. The planet is warmer. The atmosphere is thicker with dust. The south polar ice cap is releasing CO2 and water as it warms. Every element of the southern summer is aligned toward enhanced atmospheric activity and, consequently, enhanced water loss. Northern summer is the opposite. Mars is at aphelion farthest from the Sunday. The planet is cooler. The atmosphere is cleaner, the dust less active. The north polar cap is accumulating CO2 frost. The general circulation is slower and more stratified. Water vapor stays close to the surface, constrained below the hygropores, unable to reach the altitudes where photodissociation would destroy it. The northern summer hygropause is the key. Normally, the northern summer hygropause sits at roughly 20 to 30 kilometers altitude. This is the ceiling, the condensation level, above which water vapor would freeze out and return to the surface before reaching the upper atmosphere. In southern summer, the hygropause rises. In years with global dust storms, it rises further. But during normal northern summer, 20 to 30 kilometers is the ceiling, and water stays below it. The August 2023 storm raised the ceiling. Not globally, the storm was regional. But the regional heating was intense enough to locally and temporarily raise the effective hygropause over a large area of the northern hemisphere, and the convective circulation generated by the heated atmosphere was strong enough to push water through the elevated ceiling and into the zone above 40 kilometers where the photodissociation begins. The ceiling can be broken, not just by global storms, not just during southern summer, by any storm intense enough, in any season, in any hemisphere. The seasonal story was not wrong. Southern summer is still the dominant period of water loss. Global storms are still the most extreme acute events. But the story was incomplete. The northern summer was not zero. It was just quieter. Until it wasn't. These results show that water loss on Mars can be triggered by strong local dust storms at any time of year. The Brines et al. 2026 paper concluded. Any time of year. Not just the active season. Not just during global events. Any time. provided the storm is intense enough. And the frequency of regional storms across the Martian year is high. Mars generates regional dust storms regularly multiple times per Martian year, in all seasons, in both hemispheres. The Martian Dust Activity Database, compiled from years of MRO imaging, documents hundreds of regional storms per Martian year. Most are too small, too brief, or occur during seasons when the atmospheric conditions do not favour deep convection and water transport to the upper atmosphere. But some are not. Some, apparently, are exactly like the August 2023 storm intense, localised, capable of punching through the hydropore's ceiling in the northern summer, capable of driving water loss at rates the models assign to the quiet season. How many such storms have occurred in the time before MAVEN's launch in 2014, in the decades before Mars Global Surveyor began systematic imaging in 1997? Before human observation of Mars dust activity began in any systematic way? We do not know. The models which previously assigned minimal water loss to the northern summer and to regional storms in general did not capture them. The pre-2023 observational record may contain similar events that were detected in dust activity data, but not cross-correlated with water vapor or hydrogen escape data from multiple simultaneous instruments. The 2026 discovery required 4 spacecraft operating simultaneously with their data analysed together. Before 4 spacecraft were simultaneously in Mars orbit, with this combination of capabilities before MAVEN, before TGO, before HOPE, the event could not have been detected in the way it was. How many such events occurred before the instrument network was complete enough to observe them? The question remains open, but the answer almost certainly is more than 0. Let us now walk through what the discovery means for the human missions being planned, in concrete terms rather than philosophical ones. The Artemis program at NASA is focused on the Moon as a stepping stone to Mars. Perseverance is collecting samples in Jezero crater for eventual return to Earth by the Mars Sample Return mission, a mission that is currently being redesigned due to cost and complexity concerns, but remains a high priority. NASA objective: SpaceX's Starship, which completed its first integrated flight test with the Super Heavy booster in April 2023 and has been progressively demonstrating more complex milestones since, is intended as the primary vehicle for both uncrewed and eventually crewed Mars missions. China's Tianwen program has stated ambitions for a crewed Mars mission by 2033. Any human Mars mission faces a fundamental logistical constraint: the rocket equation. Getting to Mars requires enormous energy, and the launch windows periods when Earth and Mars are aligned in their orbits to minimize the travel time and fuel requirement occur approximately every 26 months. Missing a launch window means waiting 2 years for the next one. This means that any crew sent to Mars is there for at minimum 1 Mars launch window cycle, potentially 500 to 600 days, and possibly significantly longer depending on the mission architecture. 500 days minimum on the surface, living in pressurized habitats, breathing recycled air, drinking recycled water, eating supplies brought from Earth supplemented by whatever in-situ resource utilization the mission can achieve. In-situ resource utilization, ISRU, in the mission planning vocabulary is the concept of using resources found on Mars to reduce the mass that needs to be launched from Earth. The most important Martian ISRU resource is water. Water for drinking, water for hygiene, water for growing food if plant growth systems are used, and most importantly, water for propellant production through electrolysis, splitting water into hydrogen and oxygen, using solar or nuclear power to create rocket propellant for the return journey. The Sabatier reaction, combining hydrogen with atmospheric CO2 to produce methane and water, combined with electrolysis, allows rocket propellant to be manufactured on Mars from local atmospheric gas and water ice. This is the ISRU concept that enables missions that do not need to carry return trip propellant from Earth. The fuel for going home is made on Mars. Water is not just a resource for human survival on Mars. Water is the feedstock for going home. This makes the accessible water ice inventory not just a quality of life concern, but a mission-critical resource. And the 2026 discovery has revised upward the rate at which that resource is being depleted by the ongoing atmospheric escape process. Again, the total polar cap inventory is enormous. The daily loss to the escape process, even accounting for the newly discovered out-of-season storm pathway, is microscopic compared to the total. No human Mars mission is threatened by the present-day water loss rate. But the principle is clear. Any ISRU water extraction on Mars is extracting water from an inventory that is being continuously and more rapidly than previously modeled drained. The resource is finite. The draining process is ongoing, and the models that previous mission planners used to calculate accessible water resources were missing a mechanism. Revised models will be written, new estimates will be made, the accessible water inventory will be recalculated, and those recalculations will be the basis for deciding where to land, what ISRU systems to deploy, and how long a given location can support sustained water extraction. Science matters. The 2026 paper, published in Communications, Earth and Environment by a team of academic researchers studying atmospheric physics, is not a mission planning document, but its conclusions will feed into mission planning documents through exactly this pathway. Revised models, revised estimates, revised decisions about where and for how long humans can live on Mars. Let us make the story of Mars's dying more concrete by walking through the timeline in reverse, from where the planet is now, backward through the catastrophe that brought it here. Today, 2026, Mars surface pressure, 600-700 pascals, less than 1% of Earth's. Average temperature, minus 60 degrees Celsius. Thin polar caps of water ice and frozen CO2. Subsurface ice deposits at mid-latitudes. Active dust storms seasonally. Ongoing hydrogen escape at 2-3 kilograms. Second baseline with episodic spikes during storms. Total water remaining, mostly locked in ice and hydrated minerals, with a tiny vapor fraction in the atmosphere. Present-day water vapor in the atmosphere, equivalent to a layer approximately 21 micrometers deep globally. 21 micrometers, about half the width of a human hair, 100 million years ago. Mars roughly the same as today. The processes operating on it are slow, and the pace of change is geological. A more oblique Mars axis tilt, which oscillates on 120,000-year cycles and was at higher values during some past periods, would have increased water transport to the upper atmosphere and accelerated hydrogen escape during those oblique phases. The planet is in the long, slow final stage of atmospheric loss. 2 billion years ago, the last possible evidence of episodic liquid water at the Martian surface. Not an ocean, not rivers. Possibly seasonal meltwater, possibly liquid water emerging from subsurface sources heated by residual geothermal activity. A planet in its final climatic twilight, cold, dry, largely frozen, but with occasional episodes of liquid water in specific locations under specific conditions, not habitable by Earth standards. Perhaps habitable by the standards of extremophile microorganisms. 3.5 billion years ago, the atmosphere is much thicker. Surface pressure perhaps 1/10 to 1/5 of Earth's thin by terrestrial standards, but enough for liquid water in warmer regions. The magnetic field has been dead for 600 million years, and the solar wind stripping has been ongoing, but there is still water. The great river systems that carved the channels visible today, the Valles Marineris Canyon system, nearly 4,000 kilometers long and 7 kilometers deep. The largest canyon in the solar system are in various stages of formation. Large lakes and possibly remnant seas exist in impact basins. The Gale crater that Curiosity rover has been exploring was a lake at this time, a lake with neutral pH water, with chemistry that Bruce Jakosky and others have described as habitable by Earth microbiology standards. 3.9 billion years ago, the magnetic field is dying or just recently dead. The Harvard analysis places this as the latest plausible date for dynamo cessation. Before this, Mars had both a magnetic field and liquid water simultaneously, the two key conditions for habitability in combination. The planet is in the late heavy bombardment period, being pounded by asteroids and comets. Despite this violence, it has a running hydrological cycle. It has rivers and seas and an ocean in the north. It has a sky thick enough with atmosphere to scatter sunlight into a blue-tinted daytime sky. It is, by the most generous possible interpretation of the evidence, a world where simple life might exist. 4 billion to 4.5 billion years ago, the early period. Mars accretes from the solar nebula. It differentiates heavy iron and nickel sinking to form the core, lighter silicates rising to form the mantle and crust. The core is liquid. The convective circulation begins. The magnetic dynamo switches on. The atmosphere starts building from volcanic outgassing, CO2, water vapor, nitrogen, sulfur compounds. The early ocean forms. The water that will eventually be lost arrives partly in the planetary accretion itself, carried in on the bodies of carbonaceous chondrite asteroids and comets that deliver volatiles to the surface. The beginning was an ocean. The middle was the dying of the shield. The end is what we observe today, an ongoing, slow, measurable, unstoppable continuation of the loss that started when the core solidified. And in the middle of this end, us, planning to land there. The 4 spacecraft currently active in Mars orbit that contributed to the 2026 discovery deserve to be named because they represent the most comprehensive orbital surveillance of any planet other than Earth, and because the fact that the discovery required 4 separate instruments on 4 separate spacecraft to be understood tells you something important about how hard it is to understand a planet's atmospheric chemistry in detail. Mars Reconnaissance Orbiter, MRO, NASA, in orbit since 2006. The Marquee camera produced the daily global map images that first captured the growth of the August 2023 storm on August 21st and 22nd, showing the dust event expanding to 1.2 million square kilometers over the northwestern Syrtis Major region. MRO's Mars Climate Sounder instrument provided detailed vertical temperature profiles of the atmosphere during and after the storm, allowing the team to track the heating of the middle atmosphere that drove the convective water transport. ExoMars Trace Gas Orbiter, TGO, ESA, Roscosmos, in orbit since 2018. The NOMAD instrument, the Nadir and Occultation for Mars Discovery Spectrometer, detected the unusual spike in water vapor at altitudes above 40 kilometers across northern high latitudes in the days following the free storm. NOMAD uses solar occultation spectroscopy measuring how sunlight is absorbed by the atmosphere as it passes through it to determine the concentration of water vapor and other trace gases at different altitudes with extraordinary precision. This instrument provided the key measurement of water at heights where it does not belong, during a season when it does not belong there. Emirates Mars Mission Hope probe, UAE Space Agency, in orbit since 2021. The unique contribution. Hope orbits Mars in a high elliptical orbit apoapsis roughly 43,000 kilometers, periapsis roughly 22,000 kilometers, that allows it to observe the planet's full disk and its full vertical atmospheric extent in a single observation. The Emirates ultraviolet spectrometer on Hope detected the enhancement in hydrogen at the exobase, the escape boundary following the storm. This was the measurement that closed the causal chain: stormwater vapor transport to upper atmosphere, photodissociation, hydrogen escape. Without Hope's orbit and its UV spectrometer, the end point of the process, the actual escape of hydrogen into space, would have been inferred from the water vapor measurements, but not directly observed in this sequence. MAVEN, NASA, in orbit since 2014, the dedicated atmospheric escape mission. MAVEN's measurements of the hydrogen corona, the cloud of hydrogen atoms extending outward from Mars into space, provided context and cross-validation for the storm-induced escape rates measured by Hope. MAVEN's decade of continuous monitoring is the baseline against which the 2023 anomaly was measured. Without MAVEN's 10 years of accumulated observations of how hydrogen typically escapes during the northern summer season, the significance of the 2023 spike, 2.5 times the previous year baseline, could not have been quantified. 4 spacecraft, 4 instrument teams, 3 space agencies from 3 different continents, representing collaboration between American, European, and Arab scientific communities. Years of archived data crossed with months of new data analysis. A paper with dozens of co-authors from institutions in Spain, Japan, Belgium, the United States, the UAE, and France. This is what it takes to watch a planet bleed. There is a harder question underneath all of this, a question that the scientists who study Mars have been circling around for decades, and that the 2026 study brings closer to the surface. If Mars is still losing water, if the loss mechanism is real, ongoing, larger than the models predicted, and active during seasons that were not supposed to contribute significantly, then how much of the remaining accessible ice is actually accessible over the timescales of human civilization? The polar caps of Mars contain a total of approximately 3.2 million cubic kilometers of ice-water ice, mixed with frozen CO2 in the North Polar Cap, primarily water ice in the South Polar Cap. This is roughly 1.2% of the volume of Earth's Antarctic ice sheet. Spread uniformly across Mars, it would form a layer 22 meters deep. This sounds like an enormous resource. It is an enormous resource. Human Mars missions, even sustained for decades, would consume a tiny fraction of this. But the question is not about the total, it is about the accessible fraction. The polar caps are at the poles by definition, the least accessible locations on Mars from a mission planning perspective. The equatorial and mid-latitude ground ice, detectable from orbit by the Sharad radar instrument on MRO, and from the surface by the Phoenix lander that directly scooped water ice in 2008 inches, the northern polar region is more accessible but more variably distributed, and at greater depths in many locations. And the dust storms, which are not optional features of Mars, not occasional inconveniences, but a fundamental and recurring feature of the Martian climate, occurring every Martian year and varying enormously in severity, threaten not just solar power generation for human habitats, as they famously threatened opportunity's survival in 2018, but now the ice itself, not catastrophically, not quickly, but measurably. Each storm that drives a spike in hydrogen escape is converting a small amount of Martian water ice into hydrogen that leaves the atmosphere permanently. The water that leaves Mars does not come back. There is no rain cycle on interplanetary scales, no mechanism by which hydrogen that has escaped into heliocentric space returns to the Martian surface. The hydrogen that left in August 2023 because of the northwestern Syrtis major regional storm is gone, permanently. The equivalent amount of water, a few hundred kilograms, perhaps a few tons, over the weeks of elevated escape following the storm, is not recoverable by any technology we can imagine. This is a rounding error in the planetary water budget, but it is the principle. Every storm, every regional event, every day the sun shines on the unshielded Martian atmosphere, the water level is going down, not up. The planet is getting drier, not wetter. The process that turned a wet world into a desert is not complete. It is ongoing. We are watching a world in the final stages of losing what made it a world in the first place. Let us address the hardest version of this question. Could Mars be saved? Not in the science fiction sense of terraforming the decades-long or centuries-long process of deliberately altering Mars's atmosphere, temperature, and pressure to make it habitable by human beings without life support. That is a different discussion and a fascinating one, and one that the current evidence about water loss makes more complicated rather than less. But in the more immediate sense, could we stop the bleeding? The answer is almost certainly no, with one critical exception. We cannot restore Mars's magnetic field. The core is solidified, the geodynamo is dead. There is no mechanism by which human technology, on any foreseeable timescale or budget, could restart convective circulation in Mars's iron core. The shield is gone and will remain gone. The solar wind will continue to strip the atmosphere. The photodissociation will continue to convert water vapor into hydrogen and oxygen. The hydrogen will continue to escape. We could, in principle, reduce the rate, shielding a portion of Mars from the solar wind using an artificial magnetic field, a large superconducting electromagnetic structure, possibly at the Mars-Sun L1 Lagrange point, has been proposed by NASA researchers and studied in preliminary modeling. Such a structure would not need to be the size of a planet. A magnetic field generated at L1 would extend to encompass Mars in a downstream bubble of protected space. The calculations suggest that a moderate magnetic field at L1 could significantly reduce the solar wind stripping rate of the Martian atmosphere. This is not a near-term technology. It is a conceptual proposal. The engineering, the power requirements, the launch mass, the maintenance and operational challenges, these are beyond current or anticipated near-term capabilities. But the physics works, at least in principle. and the discovery that the present-day water loss rate is higher than models predicted that the 2026 study has added a new mechanism to the budget, makes the eventual development of such technology marginally more urgent in the long-term context of Mars occupation. But even without an artificial magnetic shield, the current water loss rate is slow enough that any human settlement on Mars would outlast it by geological epochs. The problem is not that the water will run out before humans arrive. The problem is that we are planning to establish a long-term human presence on a planet whose water inventory is irreversibly declining, and we now know that decline is larger and more continuous than we thought. Let us take a detour into what Mars looked like, specifically before it looked like this. Because the present-day dying acquires its full weight only when set against the fullness of what was lost. Mars, at approximately 3.8 to 3.5 billion years ago, the Hesperian period, the second great epoch in Martian geological history following the Noachian, was a world in transition. The Noachian had been the wetter epoch, abundant liquid water, active river systems, perhaps a persistent ocean in the northern lowlands. By the late Hesperian, the magnetic field was dead, the atmosphere was thinning, the climate was cooling and drying, but it was not yet finished. The surface retained extensive volcanic activity. Olympus Mons and the other Tharsis volcanoes, the largest volcanic complex in the solar system, were actively erupting, pouring lava flows across the surface and releasing enormous quantities of volcanic gases into the atmosphere. CO2, water vapor, sulfur dioxide. These volcanic emissions were, paradoxically, among the last things sustaining Mars's atmosphere and potentially maintaining episodic liquid water through the greenhouse warming effect of the CO2 and water vapor released. The Valles Marineris canyon system was forming. The leading theory for its formation is not erosion by water, as you might assume for a canyon of its size, but tectonic stretching and collapse of the crust, associated with the enormous weight of the Tharsis volcanic bulge pulling at the adjacent terrain. Subsequent water erosion deepened and widened the system, but the initial structure was more geological than hydrological. The large impact basins from the late heavy bombardment, including Hellas Planitia in the south and Argyre Planitia, had already formed, and were filling with sediments carried by water flowing from the surrounding highlands. Hellas Planitia, the deepest basin on Mars at 7 kilometers below the mean surface elevation, would have had a significantly higher atmospheric pressure at its base, enough higher that liquid water could potentially have existed there long after it had become impossible at higher elevations. The Jezero crater that Perseverance is currently exploring was, during the Hesperian, a lake. A river now visible as the delta structure that drew mission planners to choose Jezero as the landing site flowed in from the northwest, carrying sediment into the crater lake. The sediments settled in layers. The water chemistry altered the minerals in those layers. Those altered minerals, clays, carbonates, sulfates, are what Perseverance has been drilling into and collecting as samples for potential Earth return. They are, in the most literal possible sense, a sample of water. Not the water itself that evaporated, sublimed, escaped, but the rock that the water made. The stone that water turned on a lathe of chemistry billions of years ago and left behind when it departed. This is why Mars sample return matters so much to the scientific community, even as its cost and complexity create political headaches. The samples Perseverance is collecting from the delta deposits in Jezero crater are samples of the water that made them. Analyzing those samples in Earth laboratories with instruments orders of magnitude more sensitive and versatile than anything that can be fit into a Mars rover would tell us the pH of that ancient water, its isotopic composition, its mineral interactions, and perhaps most importantly, whether organic chemistry consistent with biological processes is present in any form. The samples are a forensic record of the water. The water is the crime scene. The samples are the evidence. If Mars sample return succeeds, it will be the most important scientific event in the history of Mars exploration. If it does not, if the mission is cancelled or indefinitely delayed, those samples will remain in their titanium tubes on the surface of Jezero crater, waiting for human hands to eventually retrieve them in the 2030s or 2040s, their secrets intact. Now let us think about what this discovery means for the question of whether Mars was ever inhabited. The habitability window on Mars is longer than once, thought the Harvard 2024 study placing the magnetic field survival at 3.9 billion years ago or later, extended the period during which Mars had both liquid water and magnetic field protection. The combination of these two conditions, liquid water and protection from stellar radiation, is the minimum we believe necessary for the origin of life as we understand it. The question of whether Mars was ever inhabited is one of the most important open questions in science. Not just planetary science or astrobiology specifically. Science in general. If life arose independently on Mars, if the prebiotic chemistry of a warm, wet, magnetically shielded early Mars produced self-replicating molecular systems, if those systems diversified into something deserving the name life, then life in the universe is not the statistical accident of Earth-specific chemistry. Life becomes something that the universe makes, given sufficient opportunity, something that happens wherever conditions permit. The evidence is equivocal. The 1996 announcement that the Allen Hills 84001 meteorite showed possible evidence of past Martian microbial life, tiny structures interpreted by some researchers as fossilized microorganisms, was not confirmed. The scientific consensus moved toward abiogenic explanations for the features in question. But the question was not closed. The meteorite is not definitive, one way or the other. The rovers have found organic molecules, the chemical building blocks compatible with biology, though not sufficient proof of biology in the sediments of ancient Martian lake beds. They have found conditions in the ancient rock that are chemically compatible with the metabolic requirements of Earth microorganisms. They have found clay minerals that can only form in the presence of neutral pH liquid water. They have found carbon isotope ratios that, in one measurement by Curiosity, produced a distribution that researchers described as potentially consistent with a biological process, though with significant uncertainty, and with non-biological explanations possible. The ongoing loss of Mars's water, the active dying that this video is about, is, in the astrobiology context, the elimination of the last surface habitats where any surviving life could exist. If life once arose on Mars, where is it now? Not on the surface, which is sterilized by UV radiation and perchlorates, and cosmic rays, and the pervasive oxidizing chemistry of the regolith. Possibly deep underground in aquifers or briny subsurface waters heated by residual geothermal activity, or in the deep crust where liquid water might still exist in pore spaces and fractures. Possibly at the base of the polar caps, where the pressure and the geothermal heat from below might maintain a liquid water interface between ice and rock. The possibility of extant Martian life surviving today in deep subsurface refugia is taken seriously by the astrobiological community, though it is considered less likely than the possibility that life existed in the past and is now gone. The ongoing water loss at the surface does not directly threaten subsurface life, if it exists. The water below ground is not being lost to the atmosphere. The mechanism of atmospheric escape operates on the water vapor in the atmosphere, not on liquid water buried kilometers below the surface. But knowing that Mars has been losing water continuously, that the process is still running, that new mechanisms are still being discovered, adds to the picture of a world in irreversible decline. A world that had more water in the past than it has now, that will have less in the future than it has today, and whose trajectory, across geological time, is one-directional. Drier, thinner, colder. Life, if it survives on Mars, is living in a habitat that is getting worse every year by the standards of what that life evolved to inhabit. The refugia are shrinking, slowly, as the available water is lost. The window is closing. There is something specific and strange about the way this discovery happened that is worth understanding, because it illuminates how science actually works at its frontier. The August 2023 event was observed in real time. Multiple spacecraft were in Mars orbit when the storm developed. Marquee images from MRO showed the storm growing on August 21st and 22nd. The data was transmitted to Earth and archived. Scientists monitoring Mars weather noticed the unusual storm. But the full significance of what was happening, the water vapor surge, the hydrogen escape spike, the causal chain from regional storm to upper atmosphere injection to hydrogen escape was not understood in real time. It was understood retrospectively, when researchers took the Marquee storm identification, the Nomad water vapor measurements from TGO, the Hope UV spectrometer hydrogen measurements, and the MAVEN hydrogen escape data, and laid them all on top of each other on a timeline, looking for correlations. The correlation was there. Days after the storm's peak intensity, water vapor surged at 40+ kilometers altitude. Days after that, hydrogen escape spiked at the exobase. The sequence was causal, not coincidental. Stormwater transport photodissociation escape. The causal chain was not observed in a single instrument at a single moment. It was assembled from 4 instruments, across days to weeks, by a team of researchers on Earth who were looking at archived data and asking, did anything unusual happen during the northern summer of 2023? Something unusual happened. This is retroactive discovery. The event occurred, the data was collected, the paper was written and reviewed and published in February 2026, 2.5 years after the storm itself. The mechanism was not understood in August 2023. It was understood in February 2026. How many events like this storm triggering out-of-season water loss by the rocket storm mechanism occurred in the years before this team thought to look for them? Before the full instrument network was in place? Before anyone thought to cross-correlate regional storm timing with hydrogen escape measurements at the exobase? We don't know, and not knowing is itself an answer. It means the water loss budget has been underestimated for as long as scientists have been estimating it. The escape models were missing a term. The term has now been identified. The estimate must be revised upward. By how much? That calculation is being done now, in 2026, by the research teams who produced the initial discovery paper, and by independent modelers worldwide who will extend the results to longer timescales and larger ensembles of storms. The answer will be in a paper or a series of papers that are probably being written right now, submitted this year or next, reviewed, published, and eventually incorporated into the standard picture. Science is slow. The event happened in August 2023. The first paper describing it was published February 2026. The full quantitative revision of the water loss budget will probably not be published until 2027 or later. And by the time it is published, there will likely be another discovery, another mechanism, another observation, another event that was unexpected, that required retroactive analysis, that added a new piece to the picture of how Mars is dying. Let us end with a different frame. Not the forensic frame, not the science frame. The frame that the angle of this story demands, the ongoing, present tense, you are watching it happen frame. Let us end with a different frame. Not the forensic frame, not the science frame. The frame that the angle of this story demands, the ongoing, present tense, you are watching it happen frame. Right now, as you watch this video, there are 5 active spacecraft orbiting Mars. There is 1 active rover on its surface. There are teams of scientists on Earth analyzing the data those instruments send back, writing papers, revising models, discovering things we did not know. The February 2026 paper was one of them. There will be more. There are always more. Somewhere on Mars's surface right now, dust is moving. A thermal gradient is building somewhere in the thin atmosphere. A convective column is forming, or has just formed, or will form in the next few hours. The Marquee camera on MRO will image it. The Nomad spectrometer on TGO may detect its effect on the middle atmosphere. MAVEN may record the effect on the hydrogen corona. Hope may measure the hydrogen at the exobase. And in the data from those instruments, the data being stored on board and eventually transmitted to Earth in the narrow radio beams that cross hundreds of millions of kilometers between a spacecraft the size of a school bus and a 70-meter dish antenna in the Mojave Desert. In that data will be the measurement of another small chapter in the ongoing dying of Mars. A planet is being killed in real time in front of our instruments, and we are sending humans to live there. Right now, as you watch this video, there are 5 active spacecraft orbiting Mars. There is 1 active rover on its surface. There are teams of scientists on Earth analyzing the data those instruments send back, writing papers, revising models, discovering things we did not know. The February 2026 paper was one of them. There will be more. There are always more. The Perseverance rover is currently on the western rim of Jezero crater, having completed its exploration of the Delta region and collected more than 23 rock core samples sealed in titanium tubes. Some of these tubes have been cached on the surface at a location called the Three Forks Depot, where they are accessible for retrieval by a future sample return lander. Others remain in Perseverance's sample handling system, ready to be collected later. Every sample tube is a time capsule from the wet Mars of 3.5 billion years ago, sitting on the surface of the dry Mars of today. The Ingenuity helicopter, a technology demonstration that arrived with Perseverance in February 2021 and was intended for just 5 flights, completed 72 flights before damage to its rotor blades in January. 2024 ended its operational phase. It demonstrated that powered flight is possible in the Martian atmosphere, despite air pressures less than 1% of Earth's. The technology it proved will inform future aerial platforms on Mars, whether survey drones for human missions or science platforms deployed from future landers. The thin atmosphere that is the product of 4.5 billion years of ongoing escape, the atmosphere that will claim more water vapor. Next time a regional storm breaks through, the hygropause is thin enough to fly in. Just barely, but enough. The Curiosity rover, a decade into its extended mission in Gale Crater, continues to drill into ancient lakebed sediments and return soil chemistry data. It detected the carbon isotope anomaly that the research team described as potentially consistent with biological processes, a result that generated significant discussion and significant caution in the scientific community. The appropriate response to an extraordinary potential finding backed by incomplete evidence. Curiosity's data continues to accumulate. It is still moving, still drilling, still asking questions. Above all of this, in Mars orbit, the instruments are watching. Marquis is taking its daily global images. Nomad is taking its atmospheric spectra. The Hope probe is measuring the hydrogen at the exobays. MAVEN is watching the escape rates in the hydrogen corona. And somewhere on the Martian surface, dust is accumulating in a region that will eventually generate another regional storm. A thermal gradient will build, a convective column will form, the dust will lift, the storm will grow. Some fraction of the time, perhaps rarely, perhaps more often than the pre-2026 models suggested, it will be intense enough, in the right season, in the right location, to push water above the hygropause, and Mars will bleed again. We will watch it happen. We will detect the water vapor surge with Nomad. We will measure the hydrogen spike with Hope. We will see the escape rate increase in MAVEN's data. We will publish a paper and revise a model and add the measurement to the growing database of evidence about how a planet dies. This is what is happening right now, not in the past tense of geological history, not in the future tense of mission planning. Right now, in the present, on a planet 200 million kilometers away, in real time. The crime is in progress. The instruments are running. The data is flowing. And someday, probably within the next decade, certainly within this century, there will be human beings on that planet breathing filtered air in pressurized habitats, looking up through a porthole at a sky, the color of faded iron, watching a dust storm build on the horizon, and knowing that somewhere above that storm, water is being blasted into space and will never come back. They will know it because we learnt it now, because the instruments were running in August 2023 when the storm developed in the northwestern Syrtis Major region, because 4 spacecraft were in the right orbits with the right instruments to detect the causal chain from storm to water transport to hydrogen escape, because an international team of scientists spent 2 years analyzing the data and wrote a paper and published it, and other scientists reviewed it and accepted it, and the discovery entered the scientific record, because we watched, because we measured, because we understood. This is why science matters, not as an abstract virtue, as a practical tool for surviving the universe, for knowing what is happening, where and why, before we commit to living in the middle of it. This is not a reason not to go. The case for Mars exploration, scientific, existential, even philosophical, is not diminished by the discovery that the planet is still losing water. The water loss rate is not an obstacle to human Mars missions on any relevant timescale. The accessible water ice reserves are enormous. The missions being planned will not be threatened by the process the 2026 paper describes. But the knowledge matters. The framing matters. When we talk about Mars as a dead world, as a tragedy in the past tense, a planet that lost its magnetic field billions of years ago and lost its water billions of years ago, and is now a static, cold, frozen relic. We are telling an incomplete story. We are making the mistake of treating the forensic evidence of an ancient crime as if the criminal stopped operating long ago. The criminal is still operating, the mechanism is still running, the water is still leaving. And there is a specific horror in knowing this that is worth naming before we close. Not the horror of imminent catastrophe, there is no imminent catastrophe. Not the horror of an unstoppable process that threatens human survival in any near-term sense. The more specific, more philosophical horror of watching something irreplaceable being lost continuously, while also planning to move to the location of the loss. The water that leaves Mars does not come back. The hydrogen atoms that escape the exobase enter heliocentric space, and eventually the broader interplanetary medium. They drift outward, dilute, become part of the background inventory of hydrogen in the inner solar system. Some may be captured by the Sunday, some may be swept up by other bodies. None return to the Martian surface from which they came. The water that Mars is losing in 2026 was on Mars for 4.5 billion years, surviving the violent Noachian bombardment, surviving the loss of the magnetic field, surviving the collapse of the ocean, surviving billions of years of ice. And it is leaving now, in 2026, because a regional storm in the northwestern Syrtis Major region in August 2023 was intense enough to push it above the hydropause, an ancient thing being lost by a recent process. A water molecule that has been on Mars since the solar system formed, in various forms: ocean water, groundwater, ice, hydrated mineral, atmospheric vapor surviving through every geological epoch Mars has experienced, finally converted to hydrogen and oxygen by photodissociation in the upper atmosphere and ejected into space because of a regional weather event that the existing climate models predicted would be too small to cause this. That is the texture of the ongoing murder. Not dramatic, not sudden, not a single catastrophic event. Slow, continuous, random in its immediate triggers but inevitable in its long-term direction. Every storm that is intense enough, every perihelion season, every solar energetic particle event that temporarily spikes the escape rate. Every day the sun shines on the unshielded Martian exosphere, and the thermal distribution places some fraction of the hydrogen atoms above the escape velocity. Day by day, water molecule by water molecule, hydrogen atom by hydrogen atom, Mars is not dead. Mars is dying. The criminal is still operating. The mechanism is still running. The water is still leaving. Mars is not dead. Mars is dying. And we just figured out, in February 2026, using data from a regional dust storm that covered 1.2 million square kilometers of the Syrtis Major region on a summer night in August 2023, one more piece of how the killing is being done. And we just figured out, in February 2026, using data from a regional dust storm that covered 1.2 million square kilometers of the Syrtis Major region on a summer night in August 2023, one more piece of how the killing is being done. Not the last piece. There will never be a last piece. The scientific record of Mars is assembled from decades of incremental discoveries, each one adding a mechanism, a constraint, a previously unknown pathway. The 2026 study joins a long line of Mars discoveries that individually seemed marginal and collectively constitute a revolution in our understanding of the planet's atmospheric evolution. The 1,999 Mars Global Surveyor, finding that the magnetic field had died more than 3.5 billion years ago. The 2008 Phoenix discovery of perchlorate in the Martian soil. The 2014 detection by Curiosity of organic molecules in ancient lake sediments. The 2018 MAVEN demonstration that the 2018 global dust storm drove a massive spike in atmospheric escape. The 2024 Harvard reanalysis pushing the magnetic field survival to 3.9 billion years ago. And now the 2026 discovery that out-of-season regional storms can trigger water escape through a pathway the models missed. Each paper, a new piece of the crime. Each discovery, a new entry in the dossier of planetary death. The dossier is growing, and every new entry makes the planet more legible, more navigable, more survivable for the people who will eventually live on it. Mars is cooperating with the investigation in the only way it can by continuing to die in front of our instruments, leaving evidence we are now skilled enough to detect and interpret. The scientists are doing their jobs. The spacecraft are doing their jobs. The planet is doing what it has been doing for 4.5 billion years, without pause, without awareness, without mercy or haste. Just physics. The researchers who contributed to this discovery deserve to be named, because behind every paper in the scientific literature are specific people who spent specific years of their lives asking specific questions and building specific instruments and analyzing specific data. Adrian Brines at the Centro de Astrobiología in Madrid, Shohei Aoki at the University of Tokyo and Tohoku University, Frank Derden at the Royal Belgian Institute for Space Aeronomy. Dozens of co-authors from institutions across Spain, Japan, Belgium, the United States, the UAE, France, Germany and Russia, representing the full international scope of Mars atmospheric science in 2026. They used instruments built by teams of hundreds of engineers across multiple national space agencies. They analyzed data accumulated across years of orbital observation. They cross-correlated measurements from spacecraft operating in different orbital regimes, using different detection methods, looking at different aspects of the same atmospheric event. And they arrived at a result that Brines described with appropriate scientific restraint as adding a vital new piece to the incomplete puzzle of how Mars has been losing its water over billions of years, and shows that short but intense episodes can play a relevant role in the climate evolution of the red planet. Short but intense episodes, at any time of year, not just the expected seasons, not just the expected storm types. The puzzle now has one more piece. The murder weapon now has one more mechanism identified. And the crime is ongoing. What does this mean for Earth? There is always a reflexive move in science communication about Mars to end with the lesson for Earth, the cautionary tale, the mirror, the "this could happen to us" conclusion, that transforms a story about another planet into a story about our own. It is a move that can feel manipulative when overdone, but in this case it is genuinely warranted. Mars's magnetic field died because its core was too small. Earth's core is larger, hotter, and has a much longer operational lifespan for the geodynamo that generates our protective shield. The Earth is not going to lose its magnetic field on any timescale relevant to human civilization. The geodynamo will operate for billions of years more. But the principle that a planet's habitability depends on its magnetic shield in ways that are not recoverable once the shield fails is not just a Mars lesson. It is a general lesson about planetary habitability. The search for habitable exoplanets has, until relatively recently, focused primarily on temperature, the famous habitable zone, and on the presence of water. The Mars story suggests that a third factor deserves equal weight: whether the planet has a sufficiently strong and sufficiently long-lived magnetic field to protect its atmosphere and water from stellar wind stripping. A planet in the habitable zone, with water, without a magnetic field, is not habitable. Mars is the proof. This reshapes the statistical picture of habitable planets in the galaxy. Planets in habitable zones are common. Planets with water are probably common. Planets with long-lived magnetic fields generated by a sufficiently large, sufficiently hot core, rotating fast enough, with the right composition may be less common, may, in fact, be a significant filter in the calculation of how many truly habitable worlds exist. The ongoing death of Mars is not just a story about Mars, it is data for the galaxy-wide calculation of how many worlds like ours there are, and why. The ongoing death of Mars is not just a story about Mars, it is data for the galaxy-wide calculation of how many worlds like ours there are, and why. Consider what the Mars story tells us about the frequency of Earth-like worlds, not just in the astronomical sense of rocky planet in the habitable zone, but in the fuller sense of rocky planet in the habitable zone with conditions capable of supporting complex life for billions of years. The Kepler and TESS missions have identified thousands of exoplanets. The number of rocky planets in stellar habitable zones is large. The statistics suggest that most solar-type stars host at least one rocky planet in the habitable zone. If habitability required only temperature and liquid water, Earth-like worlds would be common, very common. The galaxy would be full of them. But habitability requires a magnetic field, and a magnetic field requires a large enough liquid iron core, rotating fast enough, with the right composition and thermal structure to sustain a geodynamo for billions of years, long enough for complex life to evolve. Earth has met this requirement. Mars has not. The difference was mass, and the difference was permanent. Of the 4 rocky planets in the solar system, Mercury, Venus, Earth, Mars only. Earth has a strong global magnetic field. Mercury has a weak one, generated by a core composition and thermal structure unique to the planet's history of intense volcanic outgassing and solar wind stripping in the innermost solar system. Venus, which is nearly Earth's twin in size and mass, has no global magnetic field, probably because its slow retrograde rotation does not generate the necessary dynamo conditions. Mars has the remnant of an ancient field, now extinct. 1 out of 4, a 25% success rate in the solar system for generating a long-lived, strong magnetic field among rocky planets. If this ratio is roughly representative of the galaxy, if 25% of rocky planets' inhabitable zones have the right properties for a long-lived geodynamo, then the frequency of genuinely habitable worlds is 4 times lower than the temperature and water-only calculation would suggest. This is not a confirmed calculation. The sample size of one solar system is too small to draw firm statistical conclusions. But it illustrates the principle. Mars, by failing to maintain its magnetic field, has provided one data point in the exoplanet habitability calculation, and that data point says not all rocky planets' inhabitable zones stay habitable. And the ongoing death of Mars, the present-day loss being revised upward by the 2026 discovery, provides another data point. The dying of an unshielded planet is a specific, measurable, ongoing process that can be monitored in real time and whose mechanisms can be studied in detail. We have a dying planet in our cosmic backyard. We have the instruments to watch it die. The knowledge we generate from watching Mars lose its water will inform our understanding of every other rocky planet whose atmosphere is being stripped by its host star. The ongoing death of Mars is not just about Mars. It is about every Mars-like world in the galaxy that was once wet and now is not. There is one more thing to say before the summary. One more dimension of this story that sits at the intersection of science and philosophy, and the particular anxiety of being a species that has ruined one planet and is now planning to colonize another. The way we talk about Mars shapes what we think is possible there. For decades, the Mars of popular imagination, and to some extent the Mars of scientific public communication, has been cast as a cautionary tale about Earth's future. Look at Mars, the story goes, and see what happens when a planet loses its protection. The magnetic field dies, the atmosphere thins, the water escapes, the surface becomes uninhabitable. If we are not careful, if we continue to strip our own atmosphere through greenhouse gas emissions, if we allow our civilization's emissions to alter Earth's climate beyond recovery, Earth might end up looking more like Mars. This comparison is imprecise but evocative. It serves an educational function. It makes the abstract threat of climate change concrete by pointing to a nearby example of catastrophic planetary change. But it also subtly mischaracterizes what happened to Mars. The primary mechanism of Mars's transition from habitable to uninhabitable was not something Mars did to itself. It was not a runaway greenhouse effect driven by Martian civilization's industrial emissions. It was not a consequence of Martian organisms altering their planet's chemistry beyond the point of recovery. Mars was killed by physics by being too small to retain a sufficiently hot core for a sufficiently long time to maintain the geodynamo that powered the magnetic field that protected the atmosphere. Mars was murdered by its own mass. The comparison to Earth's climate future is therefore somewhat misleading. Earth is not at risk of losing its magnetic field because of human activity. The geodynamo operates on timescales of billions of years and is not susceptible to the kinds of perturbations that human civilization can produce. The risk to Earth from climate change is real and serious, but it operates through entirely different mechanisms: greenhouse warming, ocean acidification, ecosystem disruption, sea level rise, not through atmospheric loss to space. Mars is a cautionary tale, but not primarily about human-induced climate change. It is a cautionary tale about the fragility of planetary habitability, about how the specific physical parameters of a planet determine whether it can retain the conditions for life over geological time. Mars had water. Mars had warmth. Mars had, apparently, enough time for the prebiotic chemistry and possibly the basic biology that life requires. And it lost it all, not because anything did anything wrong, but because it was slightly too small. The cosmic arbitrariness of this, the fact that the difference between a dead planet and a living one could be a matter of size, of whether the core was large enough to convect for long enough, is one of the more unsettling implications of the Mars story. And the discovery that the dying is ongoing, that the loss mechanism is active, that we are only now understanding its full scope and seasonality, this adds urgency to the question of what it means to colonize a world in the final stages of its habitability decline. We are not colonizing a dead world, we are colonizing a dying one. The distinction matters. A dead world is static, its resources are fixed, you know what you are getting. A dying world is dynamic, its resources are being depleted. The timeline of habitability is active, not historical. What is possible today may not be possible in 100,000 years, or 1 million, or 10 million. On the timescale of human civilization, even on the optimistic assumption that technological civilization on Earth persists for 10,000 years, which would require a performance significantly better than any previous civilization has managed, the water loss rate is not a threat to Mars colonization plans. The accessible ice is enormous. The loss rate is tiny. The math is comfortable. But on the timescale of the solar system, on the timescale of whether Mars is a long-term home for life, human or otherwise, the trajectory is clear and it is downward. The planet is getting drier. The atmosphere is getting thinner. The process is not reversible on any timescale human technology can influence. The mechanisms are fundamental physics. The crime is ongoing. We understand more of it now than we did. We will understand more of it soon. And we are planning to move there. So here is where we actually are. A paper published in Communications, Earth and Environment, on the 2nd of February 2026, by a multinational team of planetary scientists using data from 4 Mars orbiters, MRO, the ExoMars Trace Gas Orbiter, the Emirates Mars Mission Hope probe, and MAVEN established something new. A regional dust storm that developed in the northwestern Syrtis Major region of Mars on August 21st and 22nd, 2023, covering 1.2 million square kilometers, drove water vapor to altitudes of 60 to 80 kilometers during the northern hemisphere summer, a season previously considered largely irrelevant to Mars water loss. The water concentration at those altitudes was 10 times higher than usual. Days after the storm, hydrogen levels at the exobays were 2.5 times higher than recorded in previous years during the same season. This was not predicted by existing climate models. This was not observed during this season in nearly 2 decades of previous Mars observation. This is a new pathway. Mars is losing water through a mechanism we did not know existed before August 2023. The planet is still being killed. It has been being killed continuously by the same slow, methodical, physics-driven process since the magnetic field died billions of years ago. And we have just discovered that the process has another arm we did not know about, another mechanism stripping the planet's water inventory at any time of year, triggered by any dust storm intense enough to push water above the hygropore's ceiling and into the photodissociation zone, where the sun's ultraviolet radiation breaks water into hydrogen and sends the hydrogen into space. There are dust storms on Mars right now. There were dust storms last week. There will be dust storms next week. Regional storms, global storms, local dust devils picking up loose material from the plains and swirling it upward into the thin atmosphere. Most of them will not be intense enough or long enough to push water into the upper atmosphere. Some of them will. Every time one does, Mars bleeds. We are watching. The instruments are on. The data is flowing. The planet is dying. And we're planning to move there. Not naively, not without awareness of the risks. The engineers and scientists and mission planners designing Mars missions know more about the planet's hostility than any generation of humans before them. They know about the radiation and the perchlorates, and the dust storms and the thin atmosphere and the freezing temperatures and the psychological demands of months-long isolation in a pressurized habitat on the surface of an alien world. They know about the water loss. The 2026 paper will be in the mission planning literature. It will be cited in habitat siting studies, in ISRU resource assessment documents, in climate risk analyses. The discovery that out-of-season regional storms can trigger water escape through a previously uncounted pathway will be incorporated into the models used to assess accessible water at candidate landing sites. Science moves into engineering, and engineering moves into decisions, and decisions determine whether the first humans to live on Mars thrive or struggle. We watch Mars die so that we can live there more safely. That is the practical meaning of all the instruments, all the orbiters, all the papers, all the models. The crime is ongoing, the instruments are watching, the humans are coming. And the more we understand about how Mars is being killed, the better prepared those humans will be to survive it. Not the dying, which no human presence will stop, but the consequences of the dying that they will have to live inside of every day on a planet actively bleeding into space.